Third normal form. So here we have a definition of third normal form. And what is a third normal form? Third normal form refers to the concept of transitive functional dependency. And that transitive functional dependency have the concept that one attribute depends on the other attributes, and the third attribute depends on the second attribute. So if that is the case, we normally call it transitive functional dependency. Normally we represent like this: x determines z, where actually x determines y and y determines z. So due to this, there we have a transitive dependency. So here you can see that SSN determines the departmental manager SSN, which is a transitive functional dependency. Why? Because SSN determines the number and D number determines the department manager SSN. But we write directly this thing. It means there is a transitive dependency. So the third normal form actually applies on those relations wherever we have transitive functional dependencies and we have to eliminate those dependencies. So SSN implies ename. This is not transitive because directly we can determine the ename from SSN, but here we cannot determine this directly. So that has an indirect relationship. Therefore, we call it transitive dependency. So you can write a definition for the third normal form, that relation R is in a third normal form if it is in the second normal form, of course, and there must be no prime attributes A in R, or you can see the non-key attributes must be transitively dependent on the primary key. No non-key attributes must be transitively dependent on the primary key. It means that the all non-key attribute must have direct dependency with the key. So there should be no transitive dependency, as I have discussed in the previous slide. So if that is the case, if that is the violation, that relation has to be decomposed. And again, if it is decomposed, you may find two or more relation. So you can observe this relation as well with various examples. So here you can say in short that in the first normal form, all attribute depend on the key. In the second normal form, all attribute depend on the whole key, not the part of the key. And in the third normal form, all attribute depends on nothing but the key, and there should be no transitive dependency. So we have various kinds of constraints or conditions related to various kinds of normal forms. The above definitions consider the primary key only. The following more general definition take into account relations with multiple candidate keys. So normally the third normal form violation normally occurs whenever we have various candidate keys in the table or in the relation. What is the candidate key? The candidate key refers to the candidate key is a key which has all the properties of the primary key, but it is not selected as a primary key. So all those attributes or a group of attributes refers to as the candidate keys. So normally there is a violation in the third normal form wherever we have the candidate key. So normally there we will find those transitive dependencies which we have to remove. So we'll move forward and see how it can be applied and how it can be used with the example. So here you can see, so we're talking about a relation schema R, which is in the second normal form. If every non-prime attribute A in R is fully functionally dependent on the every key of R. So you can see the figure 14.12, which we referred earlier on. We can see here as well, this figure 14.12, you can see here, we have a relation that is lots, and lots has certain attributes: the property ID, the county name, the lot number, the area, the price, and the tax rate. So here you can see the property ID determines county name. Actually, according to this FD, all these dependencies based on the property ID. But actually, the county name determines the property ID, the county name and lot number determines the area, and similarly, the county name determines the tax rate, and the area determines the price. So you can see that we have various different kinds of dependencies, and there you can also see that there are transitive dependencies as well. Since this relation is only having a single attribute key, so normally second normal form violation is not there. So here we have different kinds of transitive dependencies. So what to do? So we have to see that how we can break the relations to represent those dependencies in the best manner. So here you can see that after decomposing it to lot 1 and lot 2, we can have a country name and a tax rate in a separate relation. And first we put the property ID, country name, lot number, area and price in the first relation. Here in this relation, there is also a transitive dependency that area determines price. So there is a transitive dependency, and the of course, so what we do, we have to come out with another relation, which is basically based on the area as a primary key, and we can determine the price. So here we can break this relation into this relation, and this relation, which says that the property ID determines the country name, determines the lot number, and determines the area as well. So here that is the way we decompose the relation. First, identifies those various dependencies, and then try to find out the way how we can decompose this, because these FDs really help us to come out with the possible decomposed relations. So that is the concept of the third normal form. So here you can see various other conditions as well. For example, consider the two conditions in definition of third normal form. A relation R is in third normal form whenever an FD X implies A holds in R, then either X is a super key of R, either X has to be a super key, or A is the prime attributes of R. So there are possible two catches of two types of violations. One where the prime attribute functionally determines the non-prime attributes, thus catches the second normal form violation due to null full functional dependency. That is the one possible way. And second is where the non-prime attribute functionally determines the non-prime attribute. This catches the third normal form violation due to a transitive dependency. So we have to clearly distinguish among these two, whether those prime attributes are fully functionally dependent on the primary key, or those prime attributes determines values of each other. If that is the case, then it is considered to be the third normal form. So in other words, we can say a relation R is in third normal form if it is fully functionally dependent on every key of R, or it is non-transitively dependent on every key of R. It means there must be no transitive dependency. There must be direct dependency on the primary key. So that is the concept of the third normal form. Then we have another kind of normal form which is represented as Boycott normal form, normally represented as B, C, and F. So that is a special kind of normal form. Therefore, it is not numbered. So that is actually, you can say, a one special situation or a case of third normal form. That is why it is represented with Boycott normal form. A relation schema R is in Boycott normal form or in BCNF if whenever an FTX implies A holds in R, then X is a super key of R. So whenever this condition holds, it means definitely X is the super key. So each normal form is strictly stronger than the previous one. Second NF is a stronger than one NF. Third NF is even stronger than second NF. And similarly, the BCNF has a more constraint, or you can say have an added condition, so it's more stronger than third NF. So all relations which are in third NF not necessarily also in BCNF. So there exists relation that are in 3NF, but they are not in BCNF. Hence, you can say that BCNF is considered to be a stronger form of a 3NF, or you can say it is a special case of 3NF. So you can see in this relation as well. Here you can see that in this relation, property determines the county name and the property determines the lot, property determines the area. But county name and lot, they both determine area, and area can determine the county name. So here we have different kinds of functional dependencies. So how we can have how we can represent those values. So here you can see that the area and the lot, you can see the area, this is the area. Area determines the county name and the lot determines the area. So area and lot are actually the independent one. So the area or lot will be represented with the property ID. And since area determines the county name, so area and county name will be represented in a separate relation. So now these two relations actually holds the definition of Boyce-Codd normal form, which were not actually resolved when we applied the third normal form. So actually, that is not actually the same transitive dependency, but you can say is a special case or stronger definition of a third normal form. So you can see in this relation as well that let's suppose if A is the key, B is the key, and C is an attribute which is a non-key attribute or a prime attribute. So A and B determine C and C determines B. Okay. So if that is the case, uh, you can say it is in third normal form but not in BCNF. Why? Because this definition is here also, which exists, which says that there is some sort of a candidate key which is there. So that has to be resolved. So this by definition follows the third normal form, but not following the BCNF definition. Okay, and you can see this example over here in this table, and you can understand the concept. Now let's suppose where we have a teach relation and where we have three attributes: student, course, and instructor. So now it's up to you how it is in 3NF and why it is not in BACNF. So let's assume if I give you this task as an assignment to find out why this relation is in third normal form and why it is not in BCNF. So you can determine the various kinds of FDs which exist over here, and then try to find out that why it is in 3NF and not in BCNF. So you have to determine the various kind of dependency. For example, student and whether the student codes determine the instructor or instructor determine the codes, or the codes and instructor determines the student. So we have to see those relations and try to find out why it is not in BCNF. So here is the explanation of this thing as well, the same example. So try to solve it yourself and try to find out, because here we have find out through two dependencies, that the student and course determines the instructor, but instructor also determine the course. So you can see in this relation that student codes will be considered as a candidate key for the relation, and that the dependencies shown follow the pattern in figure 4.313b, which we have represented earlier on. A relation not in BCNF should be decomposed so as to meet this property. So whatever the relation which does not follow the BCNF has to be decomposed, because in the process of normalization, whenever we apply the normal form, we have to break those relations. So again, that is being applied. So three possible decompositions are there. Either you can opt for D1, D2, or D3. In the D1 case, you can have one table for a student and instructor, and the second table for student and course. For the D2, you can have instructor as a key and course as an attribute, and course student can be appeared. So there are three possible combinations. So as a homework, you must take this table with yourself and try to break this as it is given, and to see whether you achieve the task, or or whether that objective is achieved or not, or still there are anomalies. So then you will understand that how this is possible. So, whenever we are talking about decomposing a relation into two or more relation, so there we have to apply a condition as well, and that condition is called lossless join or non-additive join, which is the testing condition for any binary decomposition. So, whenever a relation is decomposed into two relation, then what you have to do? You have to apply a non-additive join and to see whether the original relation can be developed or not, whether the original dependencies can be preserved or not. So those must be preserved. So here that is the concept of the that property which is called lossless join or non-additive join. So a decomposition D, let's suppose R1 comma R2 of R has the lossless join property with respect to set of functional dependencies which are given there in your design on or if and only if either of the FD holds. And what are those FD holds? That you take the intersection of R and R1 and R2, which implies R1 minus R2 is in F plus, or you can take the intersection of R1 and R2, or you can subtract R1 from R2. So whether one of these functional dependencies will be true if we have that property. So if you apply the non-additive join that or the lossless join property test to the three decomposition of the teach relation as we have discussed earlier on. So D1 gives the student implies instructor or student implies course, none of which is true, which is there. D2 gives the course implies instructor or course implies student, none of which is true. You can check it out as well. You can test it out taking that relation into consideration. However, D3 we get instructor implies course or instructor implies student. Since instructor implies course is indeed true, the NJB property is satisfied and D3 is determined as a non-additive good decomposition. So out of these three D1, D2, D3, D3 fulfills this testing criteria of lossless join or non-additive join property, and therefore that is applicable over here. The last functional dependency which we'll discuss in this topic is called the fourth normal form, and normally it is represented as multi-valued functional dependency, and it is normally determined with double arrow. Here you can see, if you can see my pointer, x double arrow y. How we read this? We read this like x multi determines y. Here we will not say x determines y. Here we will say x multi determines y is specified on the relation R where x and y are both subset of R. Specifies the following constraint on any relation state R of R. If two tuples T1 and T2 exist in R such that T1x is equal to T2x, then the two tuples T3 and T4 should also exist in R with the following properties where we use Z to denote R2x union Y. So here it is possible that T3x is equal to T4x is equal to T1x is equal to T2x, or T3y is equal to T1y and T4y is equal. So we have repeated values which are there in the tables. So MVD is also called trivial MVD where y is a subset of x. So in other words, you can define this as this in this way, that a relation schema R is 4NF with respect to a set of dependencies F if for each non-trivial functional dependent multi-valued dependency X multi-determines Y in F plus X is a super key for R. So here you can see the relation A first. If you can see the A, there are multi-dependency. Check E name and P name. So Smith determines X. Smith determines X. It is coming twice. You can see Smith determines Y. Smith determines Y. So there is multi-value dependency. That is called multi-value dependence. Similarly, you can see E name determines multi determines D name. See in the A table. So X determines John, X determines Anna, Y determines Anna, Y determines John. So there is also the multi-value dependency. So what we have to do, we have to decompose this relation, and you can see how this relation can be composed. That E name and P name comes in this relation, and E name and D name will come in this relation. So that relation is decomposed into two. Now we have this definition that that table is converted into employee project and employee dependent. Similarly, take this relation into an example. This is the first example, this is the second one, supply. Here we have the supply name, part name, and project name. All these three are keys. No prime key, no non-key attribute is there. So here Smith determines bold, Smith determines nut, and Emsley dependent nail and Emsley dependent bolt. Again, there is a multi-value dependency. That is, we are talking about C. So there are multi-value dependency. How this can be broken up? So you can see that relation is decomposed into three relations: S name, part name, S name, and project name, and part name and project name. So now in these three relations, there is no anomaly and there is no multi-value dependency. But in this relation, we have observed the multi-value dependency, which creates that anomaly, and that has to be sorted out. That is basically the definition of fourth normal form. So with this, I conclude here the concepts of normal form, which includes the basic definitions and guidelines for the design. Then we have discussed the functional dependency, normal forms, and then in the end, we have discussed also the BCNF and the fourth normal form. So please go through with the chapter in detail and try to attempt those exercises. Thank you.